And the next talk will be given by Dmitry Indeitsev, corresponding member of Russian Academy of Sciences and from the Institute for Problems in Mechanical Engineering. So, Dmitry Anatolyevich, you have...
It's, as you know, I'm sorry, it will be our young colleague, Vavilov, young colleague, will do this report. I'm sorry.
Okay, Dmitry Vavilov.
Yes, good morning, dear colleagues.
Oh, here, you see him. You see him.
Yes.
Can everybody hear me, yeah?
Yes, we can hear you.
Good. Now I can start the demonstration. So can everybody see the presentation?
Yes.
Yeah, great. Then
It's well. It's well.
So now I'll start. So today we'll talk about the linear thermal expansion coefficient, as you can see from the title. But I will start from some basic principles of mechanics. So, well, it's a decomposition of stress tensor into spherical parts and the deviator. So you can see here. Now we'll focus our attention on the spherical part. It is determined by the variation of particle concentration. And from the balance equation, and if we could take into account the source term on the right-hand side, on the right side of this equation, we actually obtain in the framework of linear theory, it's the Gamel-Newman relation. It is also very often used in analysis of thermomechanics, but still we're not fully satisfied with this relation. So 2 words about some experiments. This experiment is about photoacoustic effect in the vicinity of a hole in ceramics and in metals. There is a famous relation about the linear thermal coefficient in case of uniaxial case. So if we take into account the temperature dependence of Young modulus, we can write here this relation. It's the dependence of this linear thermal coefficient on stress, on external stress. So he's here sigma 1. Usually, as we know, this derivative temperature of Young modulus is less than 0, it's negative. So we expect for the tensile stress that this coefficient will increase in comparison with initial value. And this is okay for ceramics. In metals and experiments, so you can see here this the scheme of experiments is laser radiation of the membrane. In the interpretation of Kirsch problem, the picture for metals was opposite. So I mean that in the place where we expect actually in the increasing of linear thermal expansion coefficient, we observe the opposite picture. Today we are not going to give a full explanation for this experiment, and frankly speaking, we don't know the exact answer. But we'll focus only on one feature which is not taken into account by the classical theory. It's the presence of defects in real material. And the one way of taking them into account is the usage of 2-component medium. So according to this theory, we assume that the concentration of material in the region of its defects is the sum of the concentration or density here of pure material here, and the density of defects. So, in according with the famous relation, we can analogous to one component medium. We can write this relation here. Parameter omega, it says takes the values. It's +1 or -1. Plus, it's if we speak about inclusions, or minus, it's for vacancies. We'll now, of course, talk only about point defects, and we won't take into account the interaction. So we need an addition equation. It's a balance of mass for defects. It is written here below, where F it's their own velocity, and F in the right side is the source of Fx depending on temperature. So it's now convenient to introduce the relative velocity, and if we assume the Picard's law that the flux of the defects is proportional to the gradient of the concentration, then we have a diffusion equation with a source term on the right-hand side. If the diffusion occupies the entire domain, I mean that's we do not take into account it now, then we can consider a relaxation model. In the framework of linear theory, we can obtain this equation. Here, tau is a relaxation time. So it's a time required to system to return to its initial state. So now after integrating this equation and substituting it into the constitutive relation, so we actually obtain this relation of the operator form, and we now it reminds us the Kelvin-Ford model. It's an operator form. It can be written in the same form as a Newman relation, but we should pay attention that now the coefficients, they're not constant. I mean the Young modulus and linear thermal coefficient, but they have a dynamical character. They depend on this relaxation time. So now a few words about the linear thermal coefficient. So we all know the theory about. So it comes from when we take into account the non-linearity form and the potential energy. And after that, so again, some few words about experiment. On the right side, you can see its dynamical character. Here it is amplitude-frequency relation taken from the experiment. It's an experiment about again the laser radiation of a very thin membrane, aluminum membrane, and we see this dynamical effects. And now we are going to consider some problem. We do not, we're not going to consider the region with the defects, but instead of this, we'll consider dynamic thermoelastic problem. It's a famous problem solved by Danilovskaya. But instead of this region, we consider the mass on the point x equal to 0 on the boundary, And now we'll try to analyze its influence on the thermoacoustic signal. Here are the equations. It's the equation for temperature, balance, momentum balance, and the only difference from Danilovskaya is the boundary condition, where we take into consideration the mass on the boundary. It's inclusion, I should say. So after that, we pass to dimensional variables, and we see that we also can obtain this relation between the strain and the temperature with the help of Laplace transform, and we can obtain the transfer function. It's written here, and here is also this amplitude frequency relation, and we see that it actually reminds us the curves from the experiments on the previous side. And here it's depicted the dependence on the relaxation time. Now we want to evaluate the influence of this inclusion on thermoacoustic signal. But before doing that, I would like to see to consider some very simple case. It's an isothermal case, so we do not take temperature now into consideration. And here in the boundary condition, the V function is now it's external pressure. It's not temperature now. So this problem is can be easily solved. It's a convolution of this function with exponential kernel, and so in this problem we can see easily the role of the time of the relaxation, which is determined, which in this problem actually is determined by the size of this inclusion divided on the velocity of sound in the medium. So the answer is very simple. It's here is depicted on the graph. So you see the blue line is a signal in the pure material without inclusion. Red line is the influence of mass, and the main thing here that we see the strong influence of inclusion. I mean the decrease of amplitude when the the duration of the pulse is rectangular pulse is comparable to the relaxation time. Otherwise, you see that the amplitude doesn't change much. So the same picture we observe actually for thermoelastic problem. So you see here it's the thermoacoustic pulse, and the same picture. The blue line for pure material, the red line for the influence of the effects. Now we go further. So this result is good enough when we talk about the small distance, so near the laser, near the source, near the thermal source. But imagine that we want to evaluate the stress and the dynamic response of material in a large distance. The problem here will, if we take the classical solution, that there are two different scales, and we'll have some problems with computing strains. In order to avoid these problems of scales, because there are two different processes here. You see, it's the propagation of sound and the propagation of temperature. they're not comparable with each other. In order to avoid this problem, we like to use methods. It's called the expansion of a variable interval. It was proposed by Leonid Slipan in 1972, so long history. Now we want to develop this method for two different processes. I mean, it's the propagation in sound and propagation of temperature, of heat wave, I should say. But few words about this method. So let's say that we have an operator, one-dimensional operator, and so we try to solve this problem using this expansion in the form of series. The only difference from Galerkin procedure is that our interval is not constant as it is usual, but it depends on time. This is here now you see below it's the criteria to determine this interval L, which is unknown. It's here's a minimum of standard deviation from the real problem, from the solution of a real problem, from our approximate one. And we can, from this, using this approach, we can obtain the equation in order to determine this unknown interval. So what do we get? I will show the usage of this method for a simple term now only for temperature problem. It's a heat conduction equation. You see flux on the boundary condition, and we will solve the approximate solution. We'll search in this form using only one term from the series, and you see the red line is an exact answer of this problem, and the blue one it's the approximation. So see that they correlate well with each other. And here is a function L. It's our variable. You see its dependence on time, and it depends on the thermodifusivity on this denoted Sk here. So after that, we can now return to our thermoacoustic problem. We need two intervals. Here you see it's L for the propagation of sound, and L here is the propagation of temperature, of heat. And it's a graph here and the intersection point. So from metals, if we put all the physical values, we see this very, very small value. It's a 10 minus 11, the power of minus 11. And now our problem is to evaluate the stress and strains in the very far, so on the right side, on the right of this on this graph, where the blue lines is above the red line, and a classical solution which works well here in this region near this intersection point. So the solution can be presented as in the form of the sum. I won't go further into details. We apply the same Galerkin procedure now, so you should see this here. The series after the Galerkin procedure, we obtain this pendulum type equation depending on the length of the interval. So, and finally, you see we can express this thermoelastic signal So these integrals on the can be calculated, but I want to see that and you pay attention again to the relaxation time, to the role of this parameter. This condition is also it's the same. The defect on the left on the boundary, it plays a big role when the duration of the pulse is can be comparable to the relaxation time. Otherwise, the amplitude doesn't change much. So, some conclusions. It's when talking, the presence of defects leads to the dynamicity of linear thermal expansion coefficient. So we need to take into account the operator form. And maybe some problems for future as taking into account the diffusion process. Of course, it's improvement of the defect model, and now we consider only some very simple model with the mass. Also, dispersion of the medium, and maybe the most interesting one last is the electron gas. So I think so that's all, and maybe some time for questions. Thank you very much for your attention. So that's all.
Thank you very much for perfect timing. So we have still about 6 minutes for questions. So do you have any? Yes, please, Professor Smirnov.
Okay, where I should look in that direction?
Yeah.
There.
Yes, I can hear you.
I see. Just the question is relevant to the model, because you introduced just multi-phase model, and so the inclusions were as a definite phase. So in the material, which has some mass, and then you suggested there was something about the diffusion of these inclusions being proportional to the gradient of their concentration. And so this, it is understandable, this Thicke's law is understandable for example, gases molecular kinetic theory, because there is chaotic motion, and so due to this chaotic motion, of course, there comes migration from the more concentrated zones to the less concentrated. But here all inclusions are, as far as I understand, surrounded by solid structure. And so what is the motivation if we have many inclusions in one place and no inclusions in the other? How they will penetrate there? So probably I missed something in the model, please.
Now we consider, we do not take you're right, we do not take the diffusion into account. We consider only very simple case. Instead of the instead of the region with defects, we just consider inclusion with mass. It's only in the boundary. So the diffusion is it's a problem for future. And in this model with the mass, we can physically feel the role of this relaxation, of this parameter relaxation time. It's just the mass of this. Yes, it's the mass of this, some size of this mass divided into the speed of sound, and that's all. So I just try to show some physical picture using this very simple model.
Okay, no, that was understandable, but my piece of advice is that before taking into account diffusion, it is necessary to find just some motivation for its existence. because now it seems to me that just the diffusion should be somehow determined in a different way in this material, not in the form of the gradient of concentrations. So there could be diffusion, but laws should be some different. Okay, thank you.
Nikolai
Thank you.
Nikolaevich,
Thank you.
Nikolai Nikolaevich, you, of course, you are right. Because for classical temperature, for room temperature, the diffusion, it's very small. And as a result, we took only the relaxation parameter as you saw from the equation. We did not take the diffusion. But we think about the diffusion of dislocation. We thought about this process.
Yeah,
What was
diffusion
this?
of dislocation, Dmitry Anatolyevich,
Yes.
I agree. The dislocation, they really, on being stressed, they diffuse following this law. But these inclusions,
yes.
material inclusions of mass, having mass, they will.
What's this mass? As you see, the surface of our solid have many different relaxant parameters. First of all, if you have a little surface with another parameters, you can see, first of all, the low frequency as a new mass, as an added mass. It's a parameter of low frequency. If we shall go in deep, we shall see another frequency for compressible situation, for stresses of this low, this surface. If we shall deeper, we shall see the diffusion, for example, dislocation. And the zoo of this relaxation parameter can take the full picture of the behavior surface material. You have the clear material, you have the surface. The first step to see the first low frequency, the influence of this surface. Now, for example, as Nikita Morozov saw the parameter of for his parameter of incubation, it's parameter incubaционный parameter for stresses.
Okay. Yeah, I see. Okay, thank you, Dmitry Anatolyevich. Now you explained me. I placed it in my mind. All your assumptions, they are on proper places. Thank you.
Thank you for your question. Thank you very much.
Okay, we also have a question from Dr. Elena Grekova. Elena, please switch on your microphone. We don't hear you. Okay. So do we still have some time? Oh. No, we need to proceed. So let's thank the speaker again. Thank you very much for very interesting presentation.
Thank you.
Just a moment. Can you hear me now?
Yeah, now we
Sorry.
can hear you. Yeah, we have some time
Yes,
for very short question. Yes.
Yes. Can we say that defects somehow trap the energy of the wave?
Initial, sorry, a bit louder because I can hear the last two words. Initial.
Can we say yes? Can we say that defects trap the energy of the wave? Trap the energy of the wave.
In some way, yes, in some way, yes, it's the process. But the situation here is a simple one because the mass is on the boundary. If it was in the, I mean, some volume distribution, of course, the problem wouldn't so easy to solve. But you're right, yeah.
Okay, so thank you very much. I think we have to continue because now we are a little bit running out of time. So thank you very much again for your very interesting presentation.